Hello students, welcome. Today we are going to learn a very important topic from Unit 13, Nuclei. The topic is mass energy and nuclear binding energy. Now, I know some of you find this a bit tricky, but I promise by the end of this class it will feel very simple and you will be fully ready for your exams.
All right, so let's jump right in. We'll start with a question, a kind of a puzzle, that might make you think, hey, that doesn't make any sense. Just think about it for a second. In our everyday lives, we always assume bigger means stronger, more stable, right? A big building is stronger than a small hut. But in the tiny world of the nucleus, something strange happens. A massive uranium nucleus is actually unstable. It's about to fall apart. But a tiny little helium nucleus, it's rock solid stable. So what's going on? Today, we are going to solve this mystery. Okay, so to solve this puzzle, we first have to understand a very strange idea. It's about what happens when things bind together. It's the secret of the missing mass. Let me give you a simple analogy. It's not perfectly scientific, but it will help you understand. Imagine two people. Person A is 70 kilograms, and person B is also 70 kilograms. If you put them on a big weighing scale separately, the total is what? 140 kilograms. Simple. But now, let's say they form a very strong bond. They become a couple. If you could weigh this couple system, you might find the weight is 139.9 kilograms. Where did that 0.1 kilogram go? Well, you can think of it like this. A little bit of mass was used up to create the energy of their bond. And believe it or not, this exact same thing happens inside a nucleus. The final nucleus, it is always lighter than the separate protons and neutrons that came together to make it. It's a fundamental rule. The whole is literally lighter than the sum of its parts. So this missing mass, it's not a mistake in our calculations. No, it is the key to everything. And in physics, we have a proper formal name for this, which you absolutely must know for your exams.
Okay, bachcho, look here. This is the official NCERT definition of mass defect. We call it delta M. It's simply the difference between the mass of all the individual nucleons, that's your protons and neutrons, and the actual mass of the nucleus once it's formed. The formula is right there. You take the mass of all protons, that's Z times MP, add the mass of all neutrons, that's A minus Z times Mn, and from that total, you subtract the real measured mass of the nucleus, which is capital M.
So the big question is, where does this mass go? It can't just vanish into thin air, right? Physics doesn't work like that. Well, the answer to this puzzle was given by none other than the great Albert Einstein.
He told us that mass is not lost. It is converted into energy. And that's what his famous equation E equals mc squared is all about. It tells us that mass and energy are, in a way, the same thing. They are interchangeable. And this energy, which comes from the converted mass, has a very important name. Nuclear binding energy, or E sub B. You can think of it as the superglue that holds the nucleus together. It's the energy that binds the nucleons. And the formula? It's so simple. Binding energy is just the mass defect, our delta M, multiplied by C squared.
Chalo, enough of theory, let's make this real with a simple calculation. We will actually calculate this nuclear glue, the binding energy, for a helium nucleus.
It's a very simple four-step process. Pay attention. Step 1, we'll find the total mass of the individual parts, 2 protons and 2 neutrons. Step 2, we'll look up the actual measured mass of the helium-4 nucleus. Step 3, we'll find the difference between them. That's our mass defect. And finally, step 4, we'll convert that mass defect into energy.
Okay, now look at the actual numbers. Step 1, the mass of the separate parts comes out to be 4.03188 U. Step 2, the actual mass of the helium nucleus is 4.00260 U. See that? It's less. The nucleus is lighter. The difference, our mass defect, is only 0.02928 U. Such a tiny number, right? But now for the magic. When we convert this tiny mass into energy, look what we get. A whopping 27.3 mega electron volts. That's a huge amount of energy from such a small amount of mass.
Okay, everyone, pens down and listen carefully. This is very important. I'm going to tell you about 2 silent killer mistakes. These are common errors students make in the exam hall and lose marks for no reason. We have to make sure you don't make them.
First mistake. Please never write in your exam that mass is lost or destroyed. That is completely wrong and you will lose marks. The correct exam-safe word is converted. Mass is converted into binding energy. Say it with me, converted. That's the word the examiner is looking for.
And the second big mistake, it takes us right back to our first question about uranium and helium. Many students think heavier nucleus means more stable. That is not true. Stability is not about total weight. It's highest for medium-sized nuclei like iron. Remember that. The really heavy ones and the really light ones are actually less stable. So you might be thinking, why is this so important? Is it just for exams? Not at all. Understanding this one idea, binding energy, unlocks the secret to the most powerful forces in the universe.
This graph you see here is one of the most important graphs in all of nuclear physics. It shows the binding energy per nucleon. See how it goes up and then comes down? The peak, right in the middle, is where iron is. That's the peak of stability. Now, this graph tells us something amazing. You can get energy by taking a very heavy nucleus, like uranium, and splitting it to move up towards the peak. That's called fission. Or you can take very light nuclei, like hydrogen, and fuse them together to also move up towards the peak. And that is fusion.
And where do we see this in action? Well, that missing mass we talked about. The energy it releases is what powers our sun. It's what makes all the stars in the universe shine. And right here on Earth, it's the same principle that runs our nuclear power reactors. It's literally a world-changing idea. All right, let's do a quick recap of the key takeaways for your exam. Point 1, a formed nucleus always weighs less than its separate protons and neutrons. Point 2, this difference in mass is called the mass defect. Point 3, mass is not lost. It is converted into nuclear binding energy, which is the glue holding the nucleus together. And finally, this entire process is the key to understanding both nuclear fission and fusion. And I'll leave you with one final thought to ponder. We saw how a tiny, tiny fraction of mass created a huge amount of energy. Now just think, how much mind-boggling energy is locked away inside a single gram of matter, like in the plastic of the pen in your hand right now.